So today, um, the main two things I wanted to cover are um, one of the labs, because at this point we've missed the last two labs because of kid sickness. Um, there was a worksheet that we missed a couple weeks ago, I believe it was. And then there was a lab we were supposed to do today, which we unfortunately cannot make up. There's no way to do that one at home. We can't make our own aspirin at home. I believe that's what was on the schedule for today. Let me double check here. I have a schedule next to my computer. Yeah, so we were doing the synthesis of aspirin today. But unfortunately we can't do that at home. But the previous one, which was going to be a VSEPR structures lab, that you can do at home. We didn't do that, right? I'm not crazy. Can someone confirm for me real quick that we did not do a VSCPR worksheet on campus?
No, we didn't.
Okay, I didn't think so. I remember doing a worksheet, and so I just wanted to make sure that it wasn't that one. Okay, so the VSCPR worksheet, I'm going to share my screen real quick. Out this way. Okay. There we go. There's the infinite regressing to nothing screen. So the VSCPR lab is this one right here. And this is available to you on the Blackboard site right now. I made it available maybe 30 minutes ago or so, something like that. So there's a new tab on the Blackboard site called Online Labs. And this should be the only thing that's available on that tab. So what I'm going to have you do to make up this particular lab is pretty much just what we would have done in class. You're just going to do it at home instead of being on campus with me working through it. So we have 8 different molecules here. Let me see, is there a way I can flip this? Don't know if I can. This might just mess it up. This might just mess up all of the formatting. Yeah, it's just going to mess up all the formatting. Never mind. Undo that. So you might have to tilt your head 90 degrees to take a look at this, but we have 4 different molecules on each page here. And for each of those 4 molecules, all you're going to do is you're going to draw the Lewis structure using just the normal Lewis structure rules. You're going to then sketch the molecule in 3D as best you can. Now, this is not an art class, so I'm not going to be taking off points if your sketch is not perfect. If your sketch is very clearly wrong, like if I look at it, I'm just like, there's no way I can see the right shape in this at all, then perhaps I would take off some points. But if there's any way, I can squint and, look from far away and like, oh yeah, that does kind of look like a 3D shape that I'm looking for, then that's all I'm looking for. I'm not going to be super picky. If the sketch is clearly just a copy of the Lewis structure, that's not okay, unless this Lewis structure matches the 3D structure, which for some of these it might actually. Yeah, I mean like the O2, like that's not going to have a complex 3D structure. It's just 2 atoms bonded together. So in that case, it would just really be a copy of the Lewis structure. But for something like the CH3Cl, like that's a 3D shape. It shouldn't be just 90 degrees everywhere. Like there's 3D depth to this molecule. So I'm looking for something close to that in the 3D sketch here. And then the other 2 things you're going to find for each molecule is the molecular shape and then whether the molecule itself is polar or nonpolar. So again, this is the molecular shape, not the electron shape, so not the electron geometry, it's the molecular geometry that you're going to put in here. And that is pretty much it for this. It's pretty simple and straightforward in terms of what I'm looking for. It's just a matter of making sure you get the right answers for each of those. And there should be on Blackboard a place where you can turn this in. Let me see if I can pull that up here. Go to the student view. So yeah, if you go to online labs, and so this is the lab here, so you can just click on that to download it. If you click on the name, it will take you here. And so it gives you a little bit of information. Obviously that due date is wrong. I'll fix that here in a minute. That was from the last time that I had to do this online instead of in person. So that due date is wrong, ignore that, but the number of possible points, that's correct. And then when you finish it, so you'll print it out and preferably write everything out. If you think you can do everything on a computer, you can feel free to try that, but that sounds like torture to me to try to draw Lewis structures in a computer, like in Word. That does not sound like fun, so I would much prefer to just print it out, fill it out by hand, and then either take pictures or scan it or something like that. And then you can just click here to upload the files, or file. If it's pictures, it'll probably be 2 files, because you'll need a picture for each page. But that's fine. You can upload more than one at a time. And then just click submit, and you will turn it in. And I will grade it online, like it'll be in Blackboard, and I can leave comments on it for stuff that I find issues with, and that should be all you need for that. Are there any questions about that lab? No questions? Sounds good. Like I said, it should hopefully be fairly straightforward. Some of those molecules we've probably already worked through the Lewis structures before, at least. Maybe even the VSEPR structure, I'm not sure. But hopefully you don't have too much trouble with that, and you can get that turned in. The only other thing I had planned to do today was just to talk about the final. So the last exam in the class, which is next week, I believe. Yeah. So we have our final exam, which next week is finals week. And by the way, I am planning, assuming that I'm not sick, I am planning on being on campus next Tuesday. So technically speaking, we do not have class during finals week. Like, you will be able to take the final at a testing center, and it'll be available all week. I believe the testing center, or at least one of the testing centers, is open on Saturday the 10th. I believe it is the 10th, right? Yes, the 10th. So I believe that at least one testing center is open the 10th. So assuming that is correct, the 10th would be the last day that the final is available. Because I have to have grades turned in by Monday morning. If I don't have grades turned in Monday morning, people from my boss's office start calling me with angry tones of voice saying, "Why are your grades not in? Get your grades turned in. They need to be turned in right now." So Saturday is the latest. The semester is actually officially over Sunday. The semester closes Sunday, but the testing centers aren't open that day. Beginning the practice test and the key as soon as I can. With all this stuff that I've been dealing with, I just have not gotten around to it yet. Hopefully I will have time today. I hope. I won't be really doing a whole lot today in terms of going out and about, probably, unless my kids get worse, and in which case I might need to take them in somewhere. But I'll still be, getting food for them, checking on them, all that stuff, and so that kind of puts a hamper on things. So hopefully I will have time today to get that up and available. As far as adding the homework to Blackboard, I seem to remember trying to do that not too long ago, and it just was not, it was not wanting to port over. If the Mastering Chemistry doesn't automatically port over, which for some reason in some of my classes it will do it, and in other classes it just doesn't want to. If it doesn't move over automatically, usually what I do is at the end of the semester I will have a single column in Blackboard where I just manually move the total over into the Blackboard gradebook, because I do have to have everything in the Blackboard gradebook, and so that would be where that would show up. Is it would just be a manual, me going in, having like two screens open where I can see your total of homework points earned, and then have the Blackboard gradebook on the other side, and just manually typing and copying from one side over into the other. I don't know why Mastering Chemistry will move the scores over for some of my classes, but then other ones it won't. I don't know what its deal is. But I know in my fully online class, it does move over the homework grades. So I don't know why it won't in other ones. But it will, no worries about missing those or me forgetting it. I promise I will not forget it. That is not possible. I will get all those moved over. They will be counted. It might just not be until all of them are finished. We have a review. We can do that review right now if you all would like. I would have to pull up some stuff here. But that would also be what we would do next week. So what I was kind of getting at there with that, talking about not technically having class next week, is assuming I am well, I'll still be on campus next Tuesday. So for anyone that is interested, again, assuming I am there and well, we can review in person on campus during the normal class time next Tuesday. And spend maybe a little bit more time working through practice problems and stuff like that as a class. But again, that is completely and totally optional. We do not have class next Tuesday. If we have missed any previous labs, will the labs not done due to sickness affect us negatively? No. So missing labs because I am sick is not going to have any negative effect on your grade. So we're still going to do the thing that I talked about, where if you made it to all the labs, you get extra credit worth your lowest lab score. That's still going to be in effect. It's just the total number of lab points available will drop by 20. You don't get points for being on Zoom, but you will get points for completing that VICPR lab that I was telling you about. Like, that will be worth a lab grade. Okay. All right. Let's go ahead and run through these really quickly then, and I will make my screen available again. Okay. So I'll do this. I'll do this pretty quick. So the first. So this is Unit 4 again. So our final is not comprehensive. It is not from everything from the entire class. It is just the last unit of chapters. So the first chapter from Unit 4 is the acids and base chapter. So as far as this stuff through here, I'll go ahead and just make this full screen. So there's a little bit of information here at the beginning, just general properties of acids and bases. Really the only thing that I expect you to know from this is that acids turn blue litmus red and bases turn red litmus blue. That's the main thing I want you to know from this. I'm not going to ask you about their taste because you should never be tasting them. Well, in the lab at least. You'll taste acids all the time just eating stuff. There's actually quite a bit of acids in foods, but in lab, you're never tasting anything. So here we're getting into the definitions. I do expect you to know the Bronsted-Lowry definition of an acid and base. So there were two different definitions that I talked about here. There was the Arrhenius definition, which is a decent and fine definition, but the Bronsted-Lowry definition is a better one in most cases. So I do expect you to know the definition of a Bronsted-Lowry acid and a Bronsted-Lowry base, and that is simply just that the acid is a proton donor and the base is a proton acceptor. So that could be a nice, easy fill in the blank or multiple choice type question. Let's see. So here we're getting into the actual reactions that are taking place. And how you have acids, bases, and then the conjugate acids and bases. Let's see. And I believe is that the let's see. So that's where we talked about those examples. I'm trying to remember everything I covered in this. This particular chapter is more difficult for me to remember what I cover because I cover this stuff in 3 different classes and it's a little different in every class. If you were in my Gen Chem 2 class, we'd be doing a lot more about this stuff in here, but we are not in Gen Chem 2. Okay. So in this section here, talking about just the reactions themselves and what takes place, I'm not going to have you like finding, you know, here's a base, what's its conjugate acid, here's its acid, what's its conjugate base. It's more so just understanding that in an acid-base reaction, there will always be an acid and a base. You can't have 2 things reacting and say, oh, they're both acids. Or 2 things reacting and say, oh, those are both bases. Like if there is a reaction happening, if there's an acid-base reaction happening, even if you have 2 things where in a different situation, both of them might behave in an acidic manner, one of them has to be the base, one of them has to be the acid. one is accepting a proton, the other one is giving up a proton. And that is always the case. All right, and these types of reactions, I do expect you to know that they're called neutralization reactions when you have an acid and a base reacting. And this is mainly true for strong acids and bases, but not necessarily. But for our purposes, we'll just say reactions between acids and bases are neutralization reactions. And so this section here, talking about strong versus weak acids and bases, mainly what I want you to know here is just the definition, the definitional difference, I guess, between the two. That a strong acid or base will completely ionize in water, while a weak one does not completely ionize. It only partially breaks apart. But I'm not going to have you memorizing the strong acids and strong bases. I have my Gen Chem 2 class memorize them, but I won't make you do that. Alright, and then for the pH scale here, what I expect you to know is that higher pHs are more basic, lower pHs are more acidic, and I expect you to be able to do very simple I'm trying to think, do we do that? I think we do, yeah. Just very simple calculations with this equation. So if I give you the concentration of H3O+, you should be able to just plug it in and find the pH. I'm not going to have you doing anti-logs, where you go the other way. If I was going to have you find the pH, I would just give you, here's the concentration of H3O+, what's the pH? And so you just plug it in and take the negative log of that. Okay. I believe that is the end of that chapter. Let me see. Heard some questions coming in. Yes, I am recording it, Jessica. So you should be able to see it on YouTube later. And there shouldn't be any issues with glitching audio or anything like that, because it looks like everything is recording correctly on my end. Because I can see the little bar jumping up as I talk, so it should be fine. I've done it before. I was so mad. I was so mad at myself because like I recorded like a whole review video, like 30 minutes long, and then I go back and like, oh, none of the audio is done. Like it's nothing that worked properly. Like the video was there, but none of the audio recorded correctly. I had to redo the whole thing. It was very sad. But it looks like it's working fine here. So we should be good. Alright, so that was the acid-base stuff there. Again, mostly in that chapter, it's just kind of memorizing some definitions, knowing, you know, the differences between acids, bases, strong acid bases, weak acid base, high pH, low pH, just kind of understanding differences. The only thing math-related there was just being able to plug in a concentration into this equation. Alright, so then the next one is the nuclear chemistry. Let me check that real quick. Before we can, I'm still having an in-person review. We can, yes. I will be there, assuming I'm well, assuming I'm not sick. I will still be there next Tuesday. It is by no means required. It is finals week, so I can't really require you to do anything except take the final. But I will be there, assuming I am well. So if you want to have an in-person review, you are more than welcome to come by and we'll work on some stuff. But for now, nuclear chemistry. Here at the beginning is just kind of an introduction. I'm not going to be testing you over Marie Curie. As far as the 4 different kinds of radioactivity, I do expect you to understand just very generally what's happening in each one of these kinds of nuclear decay. So you have the alpha decay, where your nucleus is spitting out an alpha particle. Beta decay, where the nucleus is spitting out a beta particle, which is an electron. Gamma decay, or gamma radiation, where your nucleus is spitting out high energy photons. And then positron emission, where your nucleus is spitting out a positron, which is like a positively charged electron. And so each of these things here, we worked through some very simple examples of writing out the nuclear decay reactions, with the exception of gamma, because nothing actually changes with that one. So I do expect you to be able to write out a nuclear decay equation. It would be relatively simple, relatively straightforward, nothing super fancy. Usually the way I ask these is either giving you the, like in word form, saying, you have uranium-237 and it decays via alpha decay. Write the nuclear equation. Or I could give you something like this. Where did my pen go? There it is. Okay. So I could give you, something like, switch that. Why is that not letting me do that? That's weird. Why won't it let me do a pen? I don't know. That's weird. Okay. Guess I can't write on it. So I might give you something like this, and have you fill in a blank. So maybe I would cover up the thorium here. So you could have this here, and you would have that
Professor
there.
Decker, I don't know if you can hear me, but we can't hear you.
Oh, you can't hear me? Unpause the recording. I paused the recording for a second. Okay, let's start that back up again. Okay. So the main thing from this section here, with the alpha, beta, and positron emission being the main ones here, is just being able to write out or fill in a basic nuclear decay equation. So if you remember, these things are always relatively simple. You have some starting material, and you only have one thing as a reactant. You'll have some particle that is being shot out of the nucleus, so it's always either an alpha particle like this one, or a beta particle like this, or a positron. So one of those is being spit out of the nucleus, and then you have whatever is left behind. And so I could ask a question where I just, like, in words describe what's happening. I could say, radon-228 undergoes beta decay, write the nuclear equation. And so in that question, I'm giving you this, because that's radon-228, and it's undergoing beta decay, so I'm giving you this. And so you already know 2 of the 3 things, and so you would just be working out what that third one is. And if you remember, the easy way to do that is just to look at the numbers. So on the left side here, we have 228 as the mass. We need to have 228 as the mass on the right as well. And since the beta particle has 0 mass, then we know this number is going to be 228. We have 88 as the number of the charge, which is the number of protons in this case. And so we need 88 on the right. And since we have -1 from the beta particle, that means that we have to have 89 with this one. So the 89 and the -1 together make 88. Okay. Give me just 1 second. I need to do something real quick. Okay, sorry about that. Let's see. Okay, I think everything's still going. All right, so this is just kind of a summary of what we were just talking about. Go ahead and open this back up again. So we have that there. When it's talking here about whether it's radioactive or not, all I expect you to know here is just that the strong force is what holds the nucleus together. Really nothing more than that. So the strong force, that's a force between neutrons and protons, and it holds the nucleus together. Not going to get any more complicated than that. So that could be, again, a nice, easy true, false, or multiple choice question. As far as half-lives, there is a decent chance I could give you a half-life question, but it would be very, very simple. It is not going to be something where you're going to be using equations or anything like that. If I gave you a half-life question, the most complicated it could be would be something like, you have 10 grams of this material that has a half-life of 2 years. How much would be left in 8 years? Like, it would be very simple math working out, well, if the half-life is 2 years and 8 years goes by, that's 4 half-lives. So I would always give you whole numbers of half-lives. And so then at that point you would just be working out, well, if we started with 10 grams and we have, I think I just figured out why it wasn't letting me write. Yes, okay, good. So, if we started with 10 grams and, we were told that 2 years is the half-life and we have 8 years going by, so that's 4 half-lives. And so that means it's going to be cut in half 4 times. So we would go from 10 to 5 to 2.5. Let's see, so that's 1.25, and then, what would that be? 0.875, maybe? I forget what that would be. But anyway, you just, the easiest way to do that is just to, on your calculator, do 10 divided by 2, and just divide it by 2 4 times. 0.625, not 0.875. So if I give you a half-life question that involves any kind of math at all, it would be just like that, where there would be some whole number of half-lives. You wouldn't be doing like a half of a half-life or anything like that. Again, if this was my Chem 2 class, then absolutely you'd be doing that, but this is not Chem 2. So we're keeping it as straightforward as we can. And so it would just be some whole number of half-lives, and you'd just be taking however many half-lives are going by and dividing your starting mass by 2 that many times to get your amount that's left over. Does that make sense? I'm not going to be having you doing radioactive decay trees like this. I do expect you to know that radon is the most common source of nuclear exposure, of radiation exposure for people. Unless you're having a lot of medical stuff happening to you. So if you're getting a lot of medical x-rays or you're getting a CAT scan or something, then radon's probably not your main source. But if you're just living your life and not having anything done like that, then radon is your number one source because it just is naturally occurring all around us. So that's all I expect you to know from that. As far as this stuff here, I'm not going to test you on how these detection methods work. That was more just for your own information. As far as fission and fusion, do I talk about fusion there? Talk about fission here. Do I talk about fusion at all? I guess I don't. So what I expect you to know from this is just that what's happening either in a nuclear bomb or in a nuclear power plant is what's called fission. And fission is where you have large atoms that are breaking apart into smaller atoms. It's not exactly the same as like the alpha decay that we saw earlier, but it's related and connected to that. So that's what fission is. So fission is taking a big atom, breaking it apart into smaller ones. And then the radio tracers through here, I'm not going to test you over those. That was more just of an interesting application of nuclear chemistry. Alright, so then the last two chapters, those of you that are taking a lot of bio classes are probably going to not be too displeased. I guess you should be relatively comfortable, at least with the last chapter. Maybe not this one, but the last one. Because it's a lot of organic bio memorizing shapes and names and things like that. Not a whole lot, or actually, I don't really think any math anywhere in any of these chapters. So the main point from these chapters is just going to be remembering groups, remembering types of molecules, and yeah, that's pretty much the main thing through here. So organic chemistry, I do expect you to know that this is the study of the chemistry of carbon. So as we go through here, there's going to be a few different kind of categories of carbon-based molecules that we're going to look at. So the first one here is hydrocarbons. I do expect you to know the difference between a saturated hydrocarbon and an unsaturated hydrocarbon. So that difference being that a saturated hydrocarbon has no double or triple bonds anywhere. It is just carbon and hydrogen with as many hydrogens on the carbon as possible. And then the unsaturated ones have fewer than the maximum number of hydrogens. So they either have some double bonds where some of the electrons are being used there to make the double or triple bonds, or aromatic compounds as well, which if you remember, those are the ring structures. So alkanes, those are the saturated hydrocarbons, where you just have a certain number of carbons in a row and just tons and tons of hydrogens attached to it. Now, I am not going to have you memorizing the names of these individual alkanes, but I do expect you to know that alkanes are the saturated hydrocarbons, and that there's just single bonds. There's no double bonds anywhere. I'm not going to have you memorizing this stuff here either. This is just kind of more of an interesting note on alkanes and how as you get longer chains, the actual physical properties of the material changes quite drastically. But they're all very flammable. Doesn't matter how many you have. can have one carbon and it's super flammable because that is methane, or you can have tons and tons and tons of carbons and it's still flammable. That's the wax, candle wax and stuff, is lots and lots of carbons in a row. Alright, so then the alkenes and the alkynes, I expect you to be able to identify those as well. So these are the unsaturated hydrocarbons, and if it has a double bond, that is an alkene. If it has a triple bond, that is an alkyne. And it does not matter where they are. They don't have to be at the beginning like you see them here. These are just kind of the most basic examples of those molecules, but they don't have to have those bonds right at the very beginning of the molecule. They could be anywhere in the molecule. And then the aromatics. So those are anytime you have any shape of ring. It does not have to be a 6-membered ring. It could be a 5-membered ring, or it could be a 7-membered ring. Those exist relatively commonly as well. There's even some 4-membered rings where there's 4 carbons in a ring. If there's any ring shape at all, bonded together in any way at all, it is aromatic. All right. So then the other thing, the other big thing at least, from this chapter are these functional groups. And I do expect you to know these functional groups. So you should be able to identify these, let's see, there's 7? Yeah, there's 7 of those. So those 7 functional groups you should be able to identify in a molecule. So something I've done in the past is I will just hand draw 2 or 3 different molecules, and I'll put into those molecules 1 or 2 of these functional groups for each of those molecules, and then the question will just simply be circle and name the functional groups. So I could put something in like, let's see, could have a carbon double bonded to an oxygen, which is bonded to another carbon, and that carbon is bonded, oops, that's the edge of the screen, never mind. So there's a hydrogen there, and maybe an OH group here. And that's off the screen, but let's pretend there's another hydrogen there. So I could draw something like this, and it would be your job to say, well, right here, that would be, and actually you would want to include that hydrogen in it as well. That would be an aldehyde, because we have a carbon double bonded to an oxygen, and the molecule ends after that because there's a hydrogen. So that's an aldehyde. And then over here, there's also an alcohol. Because anytime you have an OH group like that, that is an alcohol group. Now those, you have to be a little bit careful with those alcohols because they can be a part of other groups, like this one. Like you have an OH inside of the carboxylic acid. But as long as that OH is not attached to a carbon that is also double bonded to an oxygen, it's just an alcohol group. It's just this one. So you have to spend a little bit of time becoming familiar with these different groups so that you can identify the groups in a molecule, because there will be a question kind of similar to that on the exam. And so really, I think the rest of this chapter is just kind of generally describing the uses of molecules that have those different functional groups. I'm not going to have you like naming and talking about the usefulness of different molecules with different functional groups. At some point I tried to kind of have you, or have a different class name some of the different things here, but really the the common thread is just they're all very smelly. Some smell better than others, but they all just smell really strongly. Organic chemistry is a very stinky field of study. Polymers, all I expect you to know from polymers is that they're very large molecules with repeating units. That's it. You're not going to be identifying specific polymers or anything like that. It's just all I expect you to know is that they are very, very large molecules, and they're made up of some unit, some group of atoms that repeats over and over and over and over and over. So like PVC is just this group here connected to another group that is identical to that, connected to another one, connected to another one. It just keeps going and keeps going for thousands, if not hundreds of thousands of units. And that is it from that. So then the last chapter is going to be kind of similar to that one, where there's just a few certain things that I want you to be able to identify here in the biochemistry. So the four main groups that we're going to look at are the carbohydrates, the lipids, the proteins, and the nucleic acids. So the first one there, the carbohydrates. I do expect you to be able to identify a carbohydrate either just from looking at the molecule itself, or maybe I could give you 3 or 4 different molecules and say which one of these is, or which one or which 2 of these are carbohydrates. Again, the main thing you're looking for here is it's carbon-based, and you have a bunch of OH groups. So if you have a bunch of OH groups, that's a really good indicator that what you have is a carbohydrate. I do also expect you to be able to tell the difference between a monosaccharide and a disaccharide. I will just simply not have space on the paper to do a polysaccharide. But a monosaccharide, you have one sugar molecule, one carbohydrate molecule. It'll have some kind of a ring structure. And a disaccharide would have 2 of those. So pretty straightforward there, just being able to tell the difference between the 2. And like I said, I just won't have space to be putting polysaccharides in. Lipids, that'll be the next one. Moving out of the carbohydrates. So these are fatty acids with a carboxylic acid tail. So you have a really long tail here that is just a usually, well, I shouldn't say usually, it's either a saturated or unsaturated hydrocarbon tail, and then on the other end you have the carboxylic acid. And so those come together to make these larger triglycerides. So again, you should be able to identify, just generally speaking, what these kinds of molecules look like, what lipids and triglycerides look like. So a lipid would be just like one of these things, and then a triglyceride is like 3 of these connected with a glycerol, which are similar to the next one here, which is the phospholipid. So the phospholipid is very much like the triglyceride that we just saw, except one of those 3 fatty acids is replaced with a phosphate group. So again, just generally speaking, knowing the difference between a phospholipid and a triglyceride is something that I'm looking for. That could be a true-false, or probably not true-false, probably a multiple-choice question or something like that. And then steroids would be the last one here for the lipids, I believe. Yeah. So being able to identify a steroid, pretty straightforward. We're just looking for this ring structure here. And this would be the only time that I would ever put something that looks like that onto the exam. So if you see a ring structure that looks even similar to this on the exam, I'm not trying to be tricky or anything and be like, I'm not gonna, instead of this, like make one of them like like a 5-membered ring instead of a 6-membered ring and be like, ha ha ha, it's not exactly the same. Like, I'm not gonna do that. If you see multiple rings connected together like that, that's the only reason I would put that in there is because I was asking a steroid question. I'm not that big of a jerk where I would be like, there's one carbon off. You didn't notice. Nothing like that. So then proteins is the next section here from the biochemistry. So these are your little molecular machines that help you live and do life. Proteins are really pretty amazing things. So again, if I would imagine most, if not all of you, have had multiple bio classes before, so I'm probably doing a really bad job of explaining this stuff. As I mentioned in the videos, biochemistry is not my strong suit. But I do expect you to be able to identify amino acids. I'm not going to make you memorize all the different amino acids. Maybe a different class that you've had made you do that. I wouldn't be surprised. But not in this class. I do, however, expect you to be able to identify different tiers of structure in a protein. So we have primary, secondary, tertiary, and quaternary structures. So the primary structure would just be the very basic sequence of the amino acids, just one after the other after the other. The secondary structure is then how you take that string and fold it. The tertiary structure is like the macro folding of that more simple structure, and then the quaternary structure is where you have more than one string coming together to make like a full-fledged protein, not just a little piece of one. So understanding that primary is the most basic fundamental structure, and it gets more complicated as you go out from there, and then also knowing the basic differences between primary, secondary, tertiary, and quaternary. So I could give you, for example, I could, cut this out, like go into Paint and pull that little piece of the image out and put it in and just say, is this an example of primary, secondary, tertiary, or quaternary structure? And you should be able to tell me that. And this would be tertiary because it's an entire string all together, but not multiple strings. Because if it was just secondary, then it would just be a little piece of the string, not the entire string, just a kind of an example portion. And if it was quaternary, there'd be multiple strings, not just one. Alright, so here, it's just looking at different examples of those different layers of structure, talking about how important the different layers are, and what holds them together. I'm not going to test you over that, over like disulfide links and hydrogen bonding. I'm not going to test you over that. So then I believe the last section, if I remember correctly, the last section of this chapter is the nucleic acids, the DNA or the RNA. We're going to focus more on the DNA here. So here we're talking about the different forms, the 4 different forms of the deoxyribonucleic acids. So we have the C and G, cytosine, guanine, and then the A and the T, the adenine and the thymine. I do expect you to know how they are paired up, and I expect you to be able to complete any chain that I might give you. So the A and the T are always paired, and the C and the G are always paired, and so I could, and I have in the past, given something like this. Like I would cut out a section of DNA chain and then said, write the complementary string. And so you don't, if I like literally cut one of these out, you don't have to like draw the shapes or anything. You could just say, well, we have A, T, G, A, T. It's just, fill in T, A, C, T, so on down the line. But I do expect you to be able to do that. And as far as the DNA replication here, there's not really anything I want to test you over there. That was more just for your own information and knowledge. And that is it. We've lost a few people. That's okay. What questions do you have? Any questions at all? Like, what do you mean? What do you mean one of the lab questions? Do you mean like one of the molecules, or specifically like one section of one of the molecules? I could do an example molecule. I don't think I'll do one from the lab itself, but I could probably come up with one that's similar. See here. Okay, let's yeah, let's do that. Let's do let's see here. Hopefully this works. So let's do C. Oh no. Yeah, let's do that. Okay. So we're gonna do C S F2. Actually, no, let's not do that. Let's not do that one. Let's do let's do C H2F2. Yeah, that should be a good example. All right, so that's the example molecule here. So again, we're trying to find four things. We're doing the Lewis structure, the 3D shape, the molecular geometry, and whether it is polar or nonpolar. So the Lewis structure for this, we're going to find that in the exact same way that we found stuff in the past. So carbon is going to be in the middle because it has the most unpaired electrons. So then we just attach everything else to it. Doesn't matter which side we put the stuff on. Alright, so we just attach everything else to that. So we have 4 valence electrons from the carbon, 2 times 1 for the hydrogen, and then 2 times 7 for the fluorine. So that gives us, let's see, 6 plus 14, 20? 20 electrons to put into our structure. So we already have 8 in the single bonds here. So then starting on the fluorines, because they're the only ones that want lone pairs out of the fluorines and hydrogens. The hydrogens are happy. They don't want any more. So we have 8, 10, 12, 14, 16, 18, 20. So we ran out of electrons, but that's okay, because everything that wants an octet has one. So that would be our Lewis structure completed. Our 3D structure will be a little bit more complicated than this, because we're not going to have all of the atoms in a plane together. If you look at the VSEPR worksheet, what you see is that if you have 4 atoms bonded to your central atom, what you're going to have for your molecular geometry is tetrahedral. Because again, if you look at that worksheet, if you have 4 electron groups around the central atom, and all of those groups are bonds, that would be a tetrahedral molecular geometry. And there's more than one way you can draw a tetrahedral shape, but the way that I always prefer to do it is to have your central atom and 2 of the things that are bonded to it in a plane together, and then the other 2 are in and out of the plane. So this is again the way that I prefer to draw it, because remember all of these are 109 degrees apart, roughly 109.5 technically. So for our actual 3D structure here, we would have carbon in the middle. Again, it doesn't actually matter which spot you put the fluorines in and which spot you put the hydrogens in. They're all the same. So we could just put the fluorines here and the hydrogens here. So these 3 are in a plane together, and then this one is coming out of the screen towards you, and this one, one of the hydrogens is coming out the screen towards you. One of the hydrogens is going back into the screen behind it. So that would be the 3D model. And so then the last question is polar or nonpolar. And so for that, you would need to look up the electronegativities. And if you look those up, if I remember correctly, carbon is 2.5, hydrogen is 2.1, and fluorine is 4. So you have to ask yourself, do you have polar bonds? And the answer to that is yes. The carbon-hydrogen is not polar, but the carbon-fluorine is very polar, because that's a difference of 1.5. And remember, you have to have a difference of at least 0.5 to have polar bonds. 0.5 and above is polar. So this one here is exactly 0.4, so it's not polar. But because we have some polar bonds, the molecule itself is polar. Sorry, shouldn't say that yet. Because we have some polar bonds, we have the possibility of it being polar. So then the next question we have to ask ourselves is our molecule completely symmetric? And it is not. There is a mode of symmetry. You could draw a line where one side of the molecule is the same as the other side of the molecule through that line, but that's not good enough. It has to be completely symmetric. And this one is not, obviously, because we have two fluorines and two hydrogens, which are different things. If they were all fluorines, then it would be nonpolar. But because there's a difference, this is indeed a polar molecule. Is that helpful? Hope it is. All right. Well, if there are no other questions, I think I will let you all go, and I'm going to go check on my kids and make sure they're still just zoned out in front of the TV. But good luck with your studying, and as always, if you have questions, feel free to email me. I will do my best to get that example exam up later today. Have a good day.